the arc is the following. First, I will talk a bit about the motivation for the kind of research question that guides this project. Then I will go over some formalisms up to the extent to which the audience is interested. I'll go into some details. Then I'll show some results and then some general comments. So I started thinking about this quite some time ago. But more recently, something that I've noticed is that large language models and the whole buzz about natural language processing, I believe, has forgotten some central aspect concerning language. A lot of the progress that has been made in trying to devise systems that in some ways capture either syntax or semantics, but the pragmatic dimension has been forgotten. So on the one hand, I've been thinking a bit about language, and I think that the pragmatic dimension of natural language has been forgotten in the way people analyze computationally or provide models for language. There's another motivation that has to do with the fact that I've worked with agent-based models, and the kind of tools that we have to have the agent-based models communicate with each other is somewhat limited. So I wanted to devise a strategy or some form in order to do that in a more complicated way. So what I take to be the core, there's a lot going on in the pragmatic dimension of language, but what I take to be the core intuition is, for me, comes from Grice in logic and conversation. And the intuition is that in most of our fruitful linguistic exchanges, we are abiding to an implicit cooperative contract, right? A covenant, a contract, a shared agreement. And the conditions of that shared agreement as a form of the cooperative principle and the quality maxim being the most important among those. Make your conversational contributions such as it's required at the stage at which it occurs, by the accepted purpose or direction of the talk exchange in which you are engaged. Or the quality maxim, which states that try to make your contribution one that is true. This is, in a way, at the core of the pragmatic dimension of language, as I see it, and this is the kind of thing that maybe LLMs and other models forget, and this is the kind of problem that I want to focus on. So let's speak for a moment on the cooperative principle, think a bit about it. The further step was to start with the cooperative principle and building into thinking about language is more, for lack of a better word, political dimension of language, is to think of that sort of covenant as a covenant which is reasonable in some degree. And when we talk of a contract as being reasonable, what we say is that the conditions of the contract are such that everyone would be willing to accept the conditions of the contract and move forward with the conditions of the contract on the condition that other people will do so, that the other parties will do so. That's what establishes a sort of equilibrium concept underlying language. And this is the kind of target that I have, sort of equilibrium concepts at the bottom line of when we have conversations. So in the particular case of the cooperative principle, that anyone who cares about the goals that are central to conversation or communication must be expected to have an interest, given suitable circumstance, in participation in talk exchanges that will be profitable only on the assumption that they are conducted in general accordance with the cooperative principle and its maxims. So at the bottom, there's a sense of reasonability. I'm not going to talk that much about reason, but I think that the notion of an equilibrium, broadly understood as a kind of thing that is stable, for example, national equilibria are stable under unilateral deviation, so a single individual has no incentive to move on the assumption that other people are doing that. Notions of that form underlie the way we regulate our communication. Now, there's different questions about this. One of the questions is about what is the rationality underpinning of this sort of covenant, but there's other kind of questions that you can ask, again, following on the biblical metaphor, is thinking about what's the origin, what's the genesis of such a covenant, what's what they call it, right? How did we evolve into it? How did we get to be the kind of chatting cooperative creatures that we turned out to be, right? That's the kind of question that I'm trying to answer, or that I'm aiming at answering. The people that, to my knowledge, best thought about this question, the origin of this kind of social agreement that sustains communication, are David Lewis and Weizsäcker-Zentrum, right? And what they did was, following the idea of an equilibrium, model some basic framing of language as a game in which the equilibria of that game are informative in one way or another. These are the famous Lewis-Skyrms signaling games, and what I will be doing here is extend the Lewis-Skyrms signaling games. Part of what happens in Lewis-Skyrms signaling games is that try to define the conditions under which a group of people, a group of agents can develop a signaling system. Namely, they can begin by exchanging signals in some way which are not initially meaningful, and by the end they end up meaningful. This is a representation of the time. Okay, good. This is a representation of the classic standard Lewis-Skyrms signaling games. This is fine. And it goes as follows. So at the beginning, there's a random variable which is binary, so it's 0 or 1. Nature flips a coin, it gets a 0 or a 1. Sender observes that coin flip. Then senders as a function that selects a signal upon having observed that coin flip. Sends that signal to receiver, which observes the signal, and as a function of the signal observed, performs an action. And then nature again takes the underlying state of nature and the action performed by receiver. Notice importantly that receiver did not observe the state of nature, and gives some payoff to both players. Now, something that is important to mention here, I don't know, I should have put it here, but it's okay. The nature of these games, and I'm going to focus on this. These are games which are matching and cooperative games. What do we mean by matching and cooperative games? By the game being cooperative is not the sense of cooperative game theory, but what I mean is that the payoffs of both players are perfectly aligned, right? So whenever one gets 1, the other one gets 1. Whenever the other one gets 0, the other one gets 0. There's no kind of cross-alignment among the incentives or the payoffs of the players. That's the cooperative side of the game. The other side of the game is that they are matching games. That means that for each unique underlying state of nature, there's a unique action that gives payoff 1 to all of the players, and the other actions give 0, and vice versa. That's for each distinct, right? So there's 2 actions, 2 underlying states, and you want to match them. Now, initially, the players have the function here does not contain any strategy on how to provide a signal that is informative about the underlying state of nature. The signal sent by sender has no content. I mean, it's a big philosophical discussion, but that's the idea. Now, the point is that if the things are set up in the right way, you will end up with the system. I mean, I'm going to explain some of these things, achieving the kind of philosophical goal of developing a signaling system in which the signal is correlated with the underlying state of nature, so that sender can send an informative signal to receiver, which decodes the signal into the proper action, and everyone gets better. Okay? If you've seen this before, I'm sorry, I just have to explain it for those of you who haven't. Now, there needs to be a learning rule, so there needs to be an adaptation for this function. This will be one of the kind of contributions or points that I'm trying to make here. And it comes in the form of this label, reinforcement learning, which is what I like and I do. And I might go into a bit of details on these methods. Okay, good. Let me see. There might be some redundancies. The point again is that the Gricean cooperative principle and quality maxim are in a way encoded in the structure of the game played with nature. The fact that the game is cooperative and the fact that the game is matching means that that the players are cooperating and then they have an incentive to match action with signal, right? Again, this is what I said before. The pairs are aligned, and the players try to match each act with a unique, each underlying state with a unique act. So this is the important assumption that Lewis-Skyrms games do in the way they think about the emergence of language with this kind of toy model. Namely, that the cooperative nature of the linguistic exchange is encoded in the cooperative payoffs of the game. This is the thing that I want to challenge. This is the point that I want to challenge. I want to say that there are cases in which the cooperative nature of the linguistic exchange thus is not necessarily encoded in the payoffs of the games. And we'll get to that. If there are questions, feel free to interrupt and so on. Now, something, there's a famous paper from 83 or so in Econometrica, quite complicated, Crawford and Sobel. And then it helps illuminate how in the Lewis-Skyrms games, the cooperative principle is encoded in the payoffs. Because assume, for the sake of the argument, so this is a complicated economics paper, but the following small argument can be illustrative. Suppose, for the sake of the argument, that players are not aligned. So when one gets 1, the other one gets 0, right? If that is the case, then as soon as sender is associating a signal with an underlying state of nature, receiver has an incentive to use a signal against them, against sender. Because it's in his own incentive or their own incentive, they are maximizing their utility, and in doing so, they decrease that. And conversely, as soon as sender is deceiving receiver, is having the receiver do that, has an incentive. When that happens, sender has an incentive to change the value of the signal in order to manipulate receiver. The point being, if the payoffs are not aligned, or the proportion of the information that the system will learn to exchange will be a function of how aligned the payoffs of the players are in this set. Right? So that's to illustrate the deep core idea that the cooperative nature is encoded in the alignment of the payoff of the players. Okay, now for the creature model that I want to discuss here. It's a bit more complicated, and effectively, if I had to stop the talk in the next 5 minutes, I want you just to take this object. Then the rest doesn't. I mean, I can go into a lot of details, but this is the simplest kind of idea. So what is going on here? And the idea is to contrast with what's going on up there. There's a couple of things that are going on in this new setup. So the new setup is the following. There's 2 agents. Each agent observes a distinct part of the world, 2 distinct random variables, both binary, for the simplicity doesn't have to be the case. Each of them has a distinctive signaling function or encoding function, namely a function that begins by looking at the world and outputting a signal. They send it to each other, right? So already here, both players are playing sender and receiver roles. It's not that the roles are fixed with one of the players. Then each player looks at the state of nature that they observe, namely A1X, and the signal that they receive, and they pick an action. And they play again with nature. The second component in this setup is that each player is playing a distinctive game, and only player 1 gets a reward here, and player 2 gets in this game, and only player 2 gets a reward in this game. So they are looking and operating. I mean, the games can, in this particular case, be a function of the whole underlying state of nature. But the important thing here is that they are operating, they are observing distinct parts of the world, and they are engaging with different parts of the world, and there's no immediate unique game structure that is associating the payoffs for one and the other, right? So the first point was that communication has a network structure rather than a linear structure. What you have is agents wandering around doing their thing, and then there's a communication channel and they can talk to each other. Agents are both encoding senders, observing nature and sending an encoding signal, and decoding, namely taking the signal and the observed state of nature and performing an action. And the other one is that the cooperation is not encoded in the payoffs of the games, insofar as they're playing completely independent games, right? So the kind of lesson of what I want to show is to think a bit about this subject and as a proof of concept show how to teach systems like this to communicate. Even though the cooperative principle is not encoded in the payoffs of the game, even though the structure is a network structure and not just a linear structure like that. This is basically the lesson, and now I'll go into the details. Yes. So show that there, with the right learning rules, so there will be a conversation about reinforcement learning in not long. A communication system can emerge in these systems. The language is a bit tricky here. So a communication system can emerge here. And talk about the right learning rules. That's a slightly heavier lifting. I'll discuss some results with different reinforcement learning rules. And then maybe at the end, just think about what is this telling us, if anything, about the emergence of communication, how communication works, and so on and so forth. Of course, very speculatively, because this is a toy model in a way. But again, in the background, what I have is that I have, on the one hand, trying to recover the, let's say, political, I don't want to say conventional because it's a bit of an orator, but contractual nature of natural language, and on the other hand, trying to have artificial agents communicate. That's what I'm trying to do here. Good questions. If there are questions, let me know. This is a thing that you need to keep in mind. That's basically what I wanted in the. So it's here in the board. That's what I have the handout. I saw the handout. And they say you cannot do magic with words. Yeah. Well, you understand. Okay, good. So now for a bit of a formal setup, there's more formats. I didn't really know the background, so I'll do my best to run over some concepts which, if you know about them, I'll explain them maybe too superficially. And if you don't know what about them, it might be too fast, so this is always the problem, but hopefully we'll get there. Before going into some definitions or some concepts here, what I want you is to get a sort of intuition. And the intuition is the following. So what I want to show is that communication can emerge in these systems even though the games are independent and the payoffs are not necessarily aligned. And what's in the background, maybe I talked about reason before. What reason allows us to do is to have a sort of regulative idea on how things would be in their best case. So what I'm trying to say is that if you stare at the game, you know what a solution looks like. A solution is one in which the cooperative principle and the quality maxim are best satisfied. It's a case in which each agent observes the world, associates a unique signal with the underlying state of the world, sense it, and the other players decode it. We know what the ideal world is. That's why reason helps us. It gets us into the big picture ideal scenario. Then, there's complications that can emerge, but we know what a solution for the game looks like, right? Now, the question is how do we define, or whether we can define an update rule, a rule for action, a rule for learning, that takes us from the not having a communication to that place. So again, this is what I just said. The solution of the problem just means that the signaling function f is maximally informative. I specify what it means to be maximally informative, and it has to do with mutual information. So I mean, it's a very natural way of doing that mathematically. And then each agent decodes that information into the right action. Okay, good. Now, once we know what the solution of the problem looks like, there are more than one that also happen in the Lewis-Skyrms game. What do I mean by that? I can associate state of nature 0 with signal A, and state of the nature 1 with signal B, or vice versa. And that's the same, right? So all of those permutations are the same. What I need is to send a unique signal whenever I observe that state of the world. I can choose among those two options. So there are several solutions, which are all kind of the same in an abstract level. And what we need is, for a proof of concept, one thing is just a different thing. For a proof of concept, what we need is to define a rule that allows the system to learn, that makes it possible for the system to learn that signal is that can take us to that solution. A different, much more complicated question is the question of defining a learning rule that has us for sure converge to the optimal solution. A rule that solves the problem, right? Now, I don't have that, and I can say more about that. It's quite complicated. It's already extremely complicated for the Lewis-Skyrms games. They've been out for 40, 50 years now, and only 10, no, maybe 20 years ago, there was a publish of optimality for that, and it's in the Journal of Statistics Dynamics. It's like extremely way beyond my ability, but also just trying to distinguish the idea that one is a proof of concept of the system can take us there, and the other one is a proof of optimality that the learning rule converges to the optimal solution. Okay, so that was the insight. From reason, we get an idea of how a solution to the problem looks like, and the task is to define a learning rule so that the agents learn that they can get there. Now let's do a bit of artificial intelligence, if you may, or how I think of it when I encode it in the system. On the one hand, when I think of artificial intelligence in this context, not of LLMs, but in this context, I think of objects or things that have these three kind of faculties or abilities. One, they have a mind, a sort of representative. We're talking very minimalistically about what a mind, or inflationary or whatever, a memory or representational mechanism. So I'll talk about that. On the other one, they access that representational or memory mechanism, and they have to make a choice on what action to perform, which signal to send or which action to execute. And finally, they execute the action, and this is a very reinforcement learning kind of setup. And then as a function of what the outcome of performing that action, they update their representational mechanism, right? They need to change the representational mechanism in the direction of the solution of the concept, of the solution of the problem. So these are kind of a bit of the backbone of the agents. So you have a representational mechanism. In this case, I'm going to use Python dictionaries. Could be an artificial neural network as a memory object, or whatever you think a neural network is. But that's one dimension. Then you have a choice rule, and then you have an update rule. And then there's a lot of literature on this. The canonical studies for the Lewis-Skyrms games have been Roth Erev reinforcement learning agents. I am going to present few learning agents, and in the footnotes or in the appendix here, there's another one which is Temporal-Difference agents, which I don't think I have the time to present here. Okay, so Roth Erev agents. Roth Erev agents, sometimes called poly agents, sometimes called URM agents, have the following structure. They have, on the one hand, a memory/representational mechanism. The memory representational mechanism, so this where the signaling function was an F, the action function was a G. The signaling function takes an observation and outputs a signal, right? So how do we encode that? Well, we encode that as a Python dictionary that takes an observation, and you have a vector associated for that observation, in which each coordinate is associated with one of the possible signals. Each of those coordinates in the Roth Erev is associated with the propensity that the agent has at that time of sending that signal upon the observation, upon that observation. A propensity interpretation. I can write it down, but I'll write something down on the board because it might be helpful. In the standard case, when you have, let's call signal 1 and signal 2, have something of this form, right? That's the kind of thing that is in memory in the computer. And then you have the same for the action, but the action takes the observation that you had at the beginning and the signal that you receive and has a vector of the length of the actions. Now, since there were two underlying states of binary underlying states of nature, there will be 4 actions because these are still matching games. And again, the idea is that these vectors are encoding the propensity that the agent will send that signal upon this observation or execute that action upon having that observation and having received that signal. Now, in Erev-Roth, the representational mechanism and the choice mechanism are kind of similar or associated because these are interpreted as propensities because the choice rule is telling you pick A. I mean, I should have put having observed ops and the signal, pick A with probability equal to the normalized weight of that, right? So this in this case it will be pick S with probability equal to the value that is here over the value of this plus this, right? So kind of normalization. Finally, so representational mechanism, choice rule, and update rule. The update rule tells you the following. The system moves forward in the chain, and then at the end, these games, for the sake of the argument in the setup here, are still matching games, right? So people want to match. So the quality maximum is encoded in the fact that the games are matching. We can discuss about that. And then if the agent accurately sent the action associated with the underlying state, they will get a reward of 1. And if not, they will get a reward of 0. At the end of the procedure, there's a back propagation, which is that you take the reward that happened at the end of the game, and then if agent observed this, send signal this, no, yes, wait. Yeah, so in the sending of had this observation and send this signal and obtain a reward of 1, then in the coordinated associated with that signal, I add +1. And if not, I add +0. That's why it's an earn. Every time that I win, I put balls in the count of the success, of the value of the success, if not. So the idea here is that the more I win playing that strategy, the more likely it is that I will continue playing that strategy, because I will have the earns increasing in that direction. Okay. There's some in the context of what I'm talking, I'm going into some of the details. The reason I'm going into some of the details here is that this paradigm is a paradigm of the Lewis-Skyrms. This is what philosophers have done extensively. This is not what computer scientists do when they talk about reinforcement learning. And I'm going to talk about the baby properly reinforcement learning, which is Q learning, which is a bit different in some ways. And part of the upshot within the conversation of what reinforcement learning method to use will be that this outperforms the previous way by a lot. So in this one, what you have is that the representational mechanism is also a vector, exactly the same, but the interpretation is different, or the kind of things that are here are different, because they are not propensities, but a value estimate. They're trying to estimate the value of the mean payoff of playing that strategy. So the same, but the vectors are not propensity vectors, but estimation vectors. Each coordinate is an estimator of the mean reward that I will get if I were to do this, roughly. Now, I can talk about this upper confidence bound. Maybe you've heard about epsilon greedy as a choice rule. Maybe not. Have you heard about epsilon greedy? No? Okay. So what this is doing is the following, in a very few words. We can discuss this in the Q&A. Is I have an estimate of how much value I will get if I play this action in this state. If it's a signal, this will be a signal and an observation. If it's an action, this will be an action, this will be a signal, comma, observation. And what this is doing is saying, I'm going to choose the one with the upper confidence bound. the confidence, so I have an estimate for the value that an action will give me. And if I play that a lot of times, then my confidence of the mean will be more accurate, which means that the confidence bound will be more narrow. If I didn't play much, my confidence bound will be much larger. So what this is doing, I mean, I can explain it in the Q&A, but it's not that important. It is important in the sense that this has systematically shown in many setups to be a very extremely good choice rule. And there's an independent discussion of this. It's an optimistic choice rule. This is the number of times I found myself in that state, and this is the number of times I played that action in that state. So again, what this is computing is the upper bound of performing that action in that underlying state. And then the idea here is that suppose the action A is better than action B, and then action B is underexplored, so the confidence bound will be higher. But as I keep choosing action B, the confidence bound will go down, and at some point, the best strategy will have the best confidence bound, right? So the idea here is a trade-off between exploration and exploitation that that is done on the basis of looking at confidence bounds. Hopefully that was more or less clear. Finally, there's the Q-learning rule. This is a cool rule because it's associated with brain processes if you haven't seen this before. So I'll say it very simplistically. So what you have here is a predictive error. If you look Nature Neuroscience predictive error, you'll find hundreds of hits of things along these lines. So what this is saying is that I have an estimate of what it is to perform that action in that state, and this is what I actually got after that episode T of performing that action in that state, and this is the difference, right? So the difference between what I got and what I expected to get. And what this is doing is saying, okay, the new estimate needs to be the old estimate, and this is something that is decreasing in the right way, in the direction of the reward that I just got. So if my reward was more than I expected, this term will be positive, and this term will be increased. If the reward that I got was less than what I expected, this will be negative, this will be negative, and this will go down. So I update in the direction of the reward. It's a different thing. You get results that this converges to the mean of the distribution if you do things well. You get results along the lines of the predictive error. In some patterns in dopamine in the brain, I think it's pretty cool and pretty interesting. Okay, hopefully that wasn't terribly boring. A bit more formalism and then I'm done. The purpose of the talk is to show that it is possible for the system, I don't know, so I mean, I'm doing very badly, I think. No, quarter past, well, okay.
You started, okay, so.
Yeah, okay. What these equations represent is the way in which you measure how much information the signals are carrying about the underlying state of the system, about the underlying states of the system. The entropy of a distribution, these are in the setup here, or the frequency distributions when you do the simulations. The entropy of a distribution is telling me the degree of uncertainty of the distribution. The mutual information, which is that equation over there, effectively is telling me how much information observing the signal provides about the observation there. So how much of the uncertainty about the observations is reduced by observing the signal, right? So it's how, and this is just a normalization. So this is the proportion of uncertainty on the underlying distribution of the observation, so these things that come from nature, is explained by the signal. So what we want is to use those rules, train the model several times through several episodes, and as the process goes forward in the learning and in the updating that I just defined before, the signals become more and more correlated with regards to the underlying state of nature. Well, if you look at the math carefully, it just means that this, which is bounded between 0 and 1, starts very low and gets closer to 1. Just to give a small insight. This is just doing the homework, doing things properly on exactly how to define what it means for a signaling system to emerge. Namely, that the signal carries information about the underlying observation. And this is what you get. Right? This is just a proof of concept by simulation argument here. So here what you get is an example of one successful simulation in which the the agents begin with signals not associated in any way with the underlying state of nature, and as the process progresses with the episodes, then the signal gets more and more meaningful and quite fast. And then you also get that is associated with the rewards that the agent get, and then this kind of shows that the agents learn to find what action to perform in which state because they get payoff 1 at the end of the process. So the F's and the G's are updated in a way such that a signaling system emerges and such that the agents learn on the one hand to encode the underlying state of nature with a signal, on the other hand to take the signal and interpret it in the right way. We have both directions, encoder, decoder, probe. Now, a couple of things here. So this is for Q-learning, not for Roth-Erev learning with upper confidence bound. Once I saw this, I had the speculation that this could work. I ran the simulation, I saw this, and I said, good. So there's a paper here, right? Because it's quite neat. I didn't know if it was going to happen. I assumed that it might happen. It's not like I have a priori reason for it to happen. And I tried it with Roth-Erev, and it doesn't work that well, because this will be one of the actions. But once I got this, is good. There's something going on here. I'm teaching the system to learn, to communicate. Now, as you might imagine, if you click around on the simulation and do a simulation another time, what you get is also pre-writing phenomena. Just to give an example, not all simulations turn out like this, right? That will be one of it. What is a pre-writing? A pre-writing situation is one in which I send a meaningful signal to Federico. Federico decodes the signal to perform a good action, but he doesn't reciprocate. So he sends a bad signal, and I cannot get information about the signal in order to perform my action. So one of the parties does that, but not the other. That could be a function of many things. For example, signals here are cheap, no cost in sending a signal. There could be other reasons. This is a particular scenario where things work well, but the system is not always like this. But this is because intuitively we see that happening. Like some people bullshit, and some people are truthful, and that's the nature of communication also.
So
Yes.
the reason why the curves look so different, the left one has many non-differentiable points in the
That's a good question. I'm not entirely sure. There's a couple of reasons here. So first of all, they are measuring different things. Right? This is reward, this is mutual information. And then there's a few mysteries that I don't really, this is what happens when you don't have a clear analytic approach to it. Like the math is not clear to me exactly. I mean, I made my best effort to model this in the math, but it's not going to have a complete story. But in principle, there are different metrics, right? So they can operate differently. The other thing is that this is smooth because it's not visual. This means so it's smooth. It's an average among the 100. So at each point you put the forward 100 mean, so that it's smooth, so that it doesn't look terrible. I mean, but it's still close, right? We can discuss that later. There's a bit more things. Okay, now I had an argument that I don't think I'm going to present now due to lack of time, but this is more of a proof of concept that uses Markov chains. It's a bit more, it's my attempt to provide an analytic analysis of this. There's something to be said, but effectively it's just a proof of concept that the system can learn. Hopefully, we can go over this if you care, but I want to focus on some results that I think are informative. But hopefully the simulation that I just showed for now is enough proof of concept. Okay, now this is the point that I said before, namely that what I just showed is a proof of concept. It's not a proof to convergence to optimality. In simulations, none of the methods that I used always converges, so I don't have any principal reason to think that there's a proof that they will take us there. So there's room for improvement on this. It's a complicated system. Okay, some results, and with this I'll quickly wrap up with the following. So I studied different scenarios. So on the one hand, this is a wild scenario and this is a standard scenario. The standard scenario is a scenario in which you have two variables, two signals. Players can be fully informative and associate a unique signal with a unique underlying state of the world, and four actions, namely, and it's a matching game. So players can match each of the underlying states of the world with each of the four actions. In the random scenario, what you have is three variables. They observe, the first player observes X and Y, the second player observes Y and Z. Then you have a random number of signals between 2 and 10. So it's already, you can have redundancy, you can have more signals than underlying possible observations, or less signals than underlying observations, and same with actions, right? And random games. So now it's not matching games anymore. Now we're in the one. Just to play around with a ridiculous scenario to see whether the phenomena that the learning rule secures some exchange of information still holds even if we are in the wild, because the world is a wild place. So that's better. The second thing is to study four setups. The question that guides the setups is the following. Does adding a communication channel improve things in every case, right? So there's four possible scenarios. One possible scenario, so there's the scenario of partial information, which is the one that we've been discussing. So players observe only part of the world, but not all of the underlying variables. Or there's full information, namely players observe all of the X and Y, or X and Y and Z. And to each of them, you can have a signaling system, so a communication channel or not. The idea there is, suppose you have partial information. What is the performance of the players? Now, suppose I add a communication channel, that's the performance increases, right? Or, and then there's more to be said. So, and then there's a lot of parameters, so I have to do some optimization. I need to find what are the best performing parameters, and for that I have to do another process, which is some kind of parameter search, which we don't need to discuss here. So just to visualize some plots here, what we have is the following. The first row corresponds to Roth-Erev, the second row corresponds to Q-learning, the first column corresponds to rewards, the second column corresponds to normalized mutual information for the case in which there were signals, but information can be partial or not. And the third column corresponds when information is partial and there's a signal. And this is a plot of that has normalized mutual information and rewards here. So let's try to correlate, and I'll go through some of the examples. Let me also have it here. So some observations. We could stare at this for quite a bit. In general, if you look at this one, including a signaling system improves the performance of the players. So maybe the resolution is not that good. But in the case of full information, they all learned, the reward was 1, so they learned the system is working well, there's no flaws in the learning procedure. Now, when the information is partial, now we're comparing green and yellow, if there's no signaling system, then you get half a payoff, which is what you would expect if they were learned to exploit half of the information that they have. But when you include a signaling system, then in this one you have a mean reward of 0.65, and in this one you have a mean reward of 0.88. So it really improves the performance of the system once you include a signaling channel, right? So they get better by communicating, which is a way of expressing the cooperative principle, what we do all the time. The performance of your learning was better here. In this column, what you get is that you get blue is the case in which information was partial, yellow is the case in which information is total, so they observe everything. The signals were pushed to have more information when information was partial, Right? There's some kind of pressure for the signaling system to be more informative, to carry more, for signals to carry more information. And again, the Roth error didn't do particularly well, but this one is also noticeable that these are kind of what's it called now? I forgot the name. Where is it? Okay, learning. Well, double peaked, right? This is multiple peaks. This has a unique peak, and that will appear. So we start seeing some emergence of some kind of structural pattern which will come up later. And then I think this is the most impressive one. So what this is telling me is that in the setup where information was partial, in Q-learning, the amount of information that the signals carry was strongly correlated, or roughly very well correlated, with how the rewards of that the players got in that set. So signal carries value in a way. There's some minor effect on the Roth area, but it's not particularly noticeable. So these are kind of the sort of results. Happy to discuss more. Hopefully we can talk about it in the Q&A. This is for the setup, which was very random in the wild. We still get some of the results that we had before, namely in general, adding a signaling system added value in the partial information setup. Furthermore, there's some hints to the idea that in the full information setup, if you use the wrong learning rule, then information becomes, signaling becomes noisy. So you actually add noise and make the players play worse, which also find kind of interesting. Again, bimodal, this is multimodal. Again, we have a kind of a multimodal distribution. This is very funny, and I don't know where it's coming from. This is extremely structured for making random games. I don't know where it's coming from. So some structure is underlying here. I've been talking to some people about where is that coming from. I'm not really sure. But we still get the point that on average, adding signals carry more information when the setup is of partial information, and that even when the setup is partial information, there is some kind of correlation between the information carried by the signal and how much reward the players obtain, right? And in fact, in this case, the Roth error seems to be doing a bit better. Yes. Okay. Now I guess I'm wrapping up. Hopefully, more or less in time. The picture that I have in mind is something like distributed systems, right? I like this quote by Lewis, languages and language. Everyone wants to be able to learn about the parts of the world that he cannot observe from himself, by observing instead the sounds of marks of his fellows who have been there, right? We are the kinds of creatures, each of us as a distinct world operates independently, and we develop this thing to just exchange information, and it's not necessary that we share some kind of we're playing some kind of game in which we have aligned payoffs and whatnot. There can be value of leisure communication in a way, just for the purposes of understanding the world better. That's the kind of intuition that I have in the back of my mind. And in general, the setups with which I work are setups in which agents resolve different problems. And the question that I had is like, well, what about if I add a communication channel with these agents? Maybe they can get better at resolving those problems. Then there's the cost of the information, but for the assumption here, signals are cheap or free. So what were the contributions? First of all, I wanted to provide a model for communication in distributed systems, generalizing Lewis-Skyrms. This is just the model, the picture. So a way of thinking about distributed system, inspired by Grice, inspired by thinking about conversations. Then to provide a proof of concept that in this model, with the right rules, communication can emerge, signaling systems can emerge, information can be transmitted, provided that we define things in the right way. Then, again, this is a conversation with people doing reinforcement learning, mostly in philosophy, which effectively amounts to saying, stop doing Roth Erev. You should be looking at what computer scientists are doing. They've been doing pretty well with reinforcement learning. In cooperative learning, it's performing much better in this setup, which is more general than the other one. And finally, I guess that, again, what I'm exploiting here is the insight that in the Lewis-Skyrms games, traditionally people thought that the cooperative dimension of the game, there's a truth dimension and the cooperative dimension. The truth dimension is encoded in the matching nature of the game. The cooperative dimension is encoded in the fact that payoffs are aligned, right? And what I'm exploiting here is that that doesn't have to be the case. The cooperative dimension of the game could be, let's say, the joint commitment to understanding the world because the games are still matching, although there's information exchange when the games are not matching and are random. And that's the idea. The idea is that social or non-instrumental conversations in which we can learn from each other can have positive externalities because we're learning about the world and that makes us better at interacting with the world, even though our incentives are independent. Very well, thank you, that's all.